Good afternoon. So I get the difficult slot, the straight after lunch slot, when actually what you want to do is go to sleep. Nice comfy seats, and so I'm going to give you that option. You may do that, but we're going to shine lots of bright lights. There are enough bright lights here. I'm not going to turn the volume down. If you can sleep through that, well done. You deserve your rest. But for everybody else, this is what we're going to talk about for the next hour. Declarative thinking, declarative practice. My name is Kevlin Henney. My goal here is to test the tracking on the camera. I was told that it automatically tracks. Do you walk around a lot? Yes, I do. So we're going to do some software testing. I often talk about software testing, but today I want to talk about something slightly different. Declarative thinking, declarative practice. My parents gave me an internet unique name before the internet existed, which was a pretty smart move. You can do the same for your kids. Make sure you Google the combination of their names. I've done this for my kids. It works. But a bit about me. I have a very strong interest in things like design patterns, software architecture, and the like. Also have a lot of interest in the detail of code. I edited 97 Things Every Programmer Should Know a few years back for O'Reilly. I was just on the stand signing copies of this. And one of the interesting recurring themes that popped up when people were contributing to this book was sort of an emergence. And I want to point out that this is, we gathered the articles in 2009 pretty much. There was already an appetite for things like functional programming, and it was very obvious in some of the items, but also in the general guidance that was offered in other items that weren't specifically about things that were functional. There was a very strong sort of declarative emphasis. And in one sense, declarative programming is something we often focus on. It's a descriptive idea. We like the idea that our code should be descriptive. But a declarative approach takes a very different view than, say, an imperative approach, of which. And we can say that functional programming, this is not strictly a talk on functional programming, although I will certainly include it, is, if you like, declarative programming is a bigger set of things, and functional programming is part of it, or overlapping with a part of it. So it has a natural sympathy. So I want to take us back in time. This is a wonderful coincidence, since the Voxed conference has just announced yesterday, if I recall correctly, that there is going to be a Vox Day at CERN. And I'd already included this quote from Tim Berners-Lee. And one of the observations that he made, and you can kind of see the dating of this, he said, computer science in the 1960s to 80s spent a lot of effort making languages which were as powerful as possible. Now, he wrote this in the 1990s, at the beginning of the 1990s, and he was focusing on things that were very simple. We're talking about HTTP and HTML here. These are effectively declarative forms. In other words, we're stating an intention directly rather than creating a full computational model. But this idea of powerful languages, we could easily extend that to the 2000s. He said, nowadays we have to appreciate the reasons for picking not the most powerful solution, but the least powerful. And this kind of goes against our instincts. I find myself on both sides of the line here. Sometimes I want something to be more powerful, more expressive, and then sometimes I actually think, you know what, we need fewer things, more primitives. Because, as he observes, you can make things, by making things less powerful, the more you can do with the data stored in that language. It is the idea, and it's a very old idea, of code as data. If you write it in a simple declarative form, anyone can write a program to analyze it in many ways. And we see this example occurs again and again. You don't necessarily have to write you can write a parser, but the point is that the parser can be relatively simple in its interpretation. It doesn't have to have a computational model, a strong computational model behind it that maps onto things like state changes. So, how far back do we go? Well, declarative approaches have been around for a very long time. Some of them have been more influential than others. This is my printout of the original Make paper. that Feldman invented basically in the late 70s. So this is interesting. I'm putting up make here, and everybody's here sitting there like, oh, I don't use make, I use ant or something like that. And it's like, well, wait a minute. Let's look at what all of these have in common, because they're structured in a particular way. What make introduced was the idea of a less powerful language, a very simple idea of creating, as is observed in the Wikipedia article, the makefile language is similar to declarative programming. This class of language in which necessary end conditions are described, but the order in which actions are to be taken is not important, is sometimes confusing to programmers used to imperative programming. The idea is that in imperative programming, you control everything. You control all the state. You control everything and how everything fits together. You deal with all of the mechanics, all of the for loops, all of the variables. You do the pluses because you're the only person anybody can ever trust. I mean, how are you going to make sure that that value increments unless you do it? Okay? You are the most important person here. You have complete control of the machine. This comes to us directly. The imperative model, imperative means to issue a command, comes to us very directly and very obviously from assembler. And and that legacy has shone through into programming languages ever since then. But the makefile approach takes a different approach. It says there will be imperative elements, but the backbone of a makefile is the declarative structure. It is the relationships. So in other words, I want to focus on relationships. That's what we're declaring, the relationships between the parts. And then we say, oh, and detail happens, as opposed to here's all the detail. And this is a sort of an inversion. Let's go back while we're in the 1970s. Nicholas Wirth, the inventor of Pascal, Modular 2, and a lot of other things. And actually, if you're interested, the guy responsible for the title Go-To Considered Harmful. The paper was written by Edsger Dijkstra, but he didn't call it Go-To Considered Harmful. It was Nicholas Wirth who gave it that name. He wrote a book in the 1970s, Algorithms plus Data Structures equals Programs. I'm guessing this probably frustrated a lot of publishers, because the idea of using symbols in your book titles is a relatively common modern concept, but perhaps not quite so common in the 1970s. But I'm going to simplify it for you. Why don't we take a different view? What about just saying data structures equals programs? Again, there's nothing new here. If we go back to the book that everybody needs to refer to and certainly read at least once in their career, The Mythical Man Month, this is quite a long way back, and he's referring to stuff in the 1960s, and he makes the observation, representation is the essence of programming. Which, I'm going to point out, sometimes you look at a piece of code. If you're looking at a large Java code base, there is a very high probability that the Java code base is what has been referred to as stringly typed. It's all strings and a few integers. We're not making the best of the possible representations. We have very weak objects, very anemic objects. There are controllers and then DTOs, and they don't really have a lot of strong declarative feel. The behavior is stacked away in large methods, but there's no kind of compositional feeling. There's no concept of a clear view of representation. And a model of representation is the starting point. As Brooks notes, he says, look, show me your flowcharts, which is nice and quaint in the 1970s. Show me your flowcharts and conceal your tables, and I shall continue to be mystified. But show me your tables, and I won't usually need your flowcharts. They'll be obvious. We can tell from the relationships between the data structures what is going on. And if we can't tell directly, we can intuit. We can make educated guesses. We can anticipate what is going on and then be unsurprised by the detail. Whereas if I just show you control flow, if I just show you procedural structure and state change, it is very difficult to discern the intent, the declarative intent of the code. Of course, we have to be a little bit cautious when we start talking about tables and say everything should be tables because, Excel is the world's most popular functional language, and Simon Peyton-Jones, who has an awful lot to do with Haskell, a lot of people automatically assume functional programming means it'll all work out perfectly. Our evidence is that most spreadsheets do not. So clearly there's a lot more to it than just saying I have a way of representing data. It needs to be intentional. It needs to have, and it needs to have a proper structure that is properly compositional and reinforces that view. So let's look at some examples of things that fall into this category. So in 97 Things, Burke Hufnagel has this lovely, makes this lovely article, put the mouse down and step away from the keyboard. There are two things that I like about this piece. One is the general advice, which is encapsulated beautifully in the title. If you are stuck with a problem, then it is very unlikely you can solve the problem with the same kind of thinking and at the same level that you encountered it. But we persist in doing it. We spend hours and hours, even days, trying to focus on it. It turns out that if that's not working, then doing more of the thing that's not working is probably not helpful. It's kind of obvious when you state it like that. So there's the idea that do something else. Put the mouse down, step away from the keyboard. I generalize this advice sometimes. I offer it to people. I say, do something that is completely different to what you're doing at the moment. If you normally drink coffee, stop. Go and get a herbal tea. Do the opposite. If you don't drink coffee, go and get yourself a good strong espresso. Yeah, do the opposite. If you normally listen to music whilst you're working, stop. If you don't normally listen to music while you're working, start. Yeah? In other words, whatever it is that you've been doing, do the opposite of it. Because you need somehow to be doing something differently to inspire different thinking. Now, the specific example, and therefore my motivation in putting this up here, the specific example that Burke uses is an example that is very, very procedural. We can go through and we can see, right, so what are we doing? We're going to try something, and we're going to try and parse a string that is called time, so it's a representation of time, I'm guessing. We're going to look at the substring 0 for 2. We're going to take the first two characters, try and convert it to an integer. If that fails, then we're going to return false. So therefore, this was not an integer, and therefore it probably wasn't a time string. Okay, great. And now we're actually going to do the parsing, and then we're going to check, because it's 12-hour time that's being used here, we're going to check that it's not greater than 12, otherwise we are going to assume that it is false. The important thing here is that there is a ... after this. This goes on for some distance. And then we get to the end and actually finally figure out, is this AM or PM? Even if I improve this by switching from 12-hour to 24-hour, it only knocks off 4 lines. There's a lot of stuff going on here. Now, some people might be satisfied with this because there's a surprising amount of code that looks like this. We call it enterprise code. Okay? And what we're doing is it's exactly what I was describing before. It's the mechanics. We're going to go through and we're going to, let's have a look at that detail, and then there's that detail, and then there's that detail, and then let's drive that detail, and then we need to hammer this small thing in, and then worry about that state change, do all of these things. It's like, what's really going on? It's not obvious. So he did as suggested. He put the mouse down, stepped away from the keyboard, came back, and there we go. That's it. A really nice, simple expression of the problem. Now, sometimes we've got to be a little bit careful with regular expressions. There is always a danger with regular expressions that you end up with, as sometimes people say, I had a problem, and then I solved it with regular expressions, and now I have 2 problems. Although sometimes you can joke about it and say, well, actually, and now I have star problems, just to generalize further. But the point here is, actually, as a description, this is everything. It's a declarative description. I'm describing the relationship between parts. It's not a fully computational model in a Turing sense, but it's a declarative sense. There is a language that allows you, there is a form that allows you to describe exactly what you want. And it is very easy, and this is the key idea, it is very easy to see whether or not this is correct. It takes a little, if you're not familiar with regexes, then it takes a moment of explanation, but then you can see quite clearly. And this is the point, is that sometimes an imperative model may be completely general purpose, but may be obscure. Whereas a declarative model, when it's well matched, will be precise, although it may take an initial moment to educate the reader. What I find interesting about this is that I could probably explain the model here quite easily to somebody who was not a programmer. This, on the other hand, I very much expect they would either fall asleep before the end or walk off. Okay? So, the observation from the Haskell homepage, many programming languages support programming in both functional and imperative style. Obviously, they're just going to say functional rather than declarative. Declarative is a larger space, but their emphasis here is very much that. But the syntax and facilities of a language are typically optimized for only one of these styles, and social factors like coding conventions and libraries often force the programmer towards one of the styles. This is what we see. Existing code bases exert a very strong pressure. So if you're managing to migrate your code base to Java 8, or you're managing to migrate bits and pieces it to some groovy stuff, or you've decided, well, this corner of the code, we might be able to do some closure or whatever. The problem is that there is a very strong force exerted by the mass of existing code. And importantly, code does not exist in isolation. It exists with people. People define that. And there are very strong cultural conventions. And sometimes that will move us away. There are obviously language limitations. There are certain limitations, for example, within Java, that mean it's very difficult to get certain kinds of immutability working perfectly. For persistent data structures, it's just built into the language that you can't do certain things. But even allowing for that, there's a whole space of style space where people get involved, and their existing habits and the forces of an existing code base have a very strong influence. So let's just take a very simple example. I'm going to pitch this one up in Groovy, because it's syntactically lighter, of how a very imperative example and move through to a more declarative view of it. This is one of those obvious standard problems that everybody has when they're programming on a day-to-day basis. I need the squares of the first 100 numbers. I mean, obviously you have that every single day while you're working on your applications. But it's small enough, but it's precise enough to be instructive. So what we're going to do, is we're going to set up an array list. We're going to set up a collection of squares. And it's going to begin with empty. And we're going to set up a counter. And we're going to call it I, because we don't want to be too revolutionary with what we're doing. And we're going to set it to 1. And then we're going to iterate round. For as long as that counter does not exceed 100, what we're going to do is we're going to add the square of the counter to the collection. And then we're going to increment the counter, because we're in charge. That's the only way you can guarantee it's going to increment properly. Now, you'll notice in that description, it's mostly about state change. What I'm doing is I'm doing a remarkable amount of state management. I'm telling people, here's a thing, and I'm going to change it. I want to set it up like this, and here's the work I'm going to do on it. If you look at it from an indentation point of view, and this is a very instructive way of viewing your code, the indentation shows you what is important, or rather it should do. If I look at this, the idea of indentation is that you say, if it's indented, it's a secondary detail. It's subordinate to something else. That's not really what's going on here, is it? At the top level, what I've said the 3 most important things in this program are the fact that there's a list of something that begins empty, the fact that there's a counter that begins at 1, and the fact that there's a loop. Those are the top level things. That's not really what this is about. I gave you what the definition of the problem was before. It's the square of the first 100 numbers. That's not visible. Now, I can improve this. So let's go for a for each loop. And here what I've done is, although I still have varying state, what I've done is I've effectively taken away the state change from I. And you might say, well, yes, I is changing as I go round. Well, yes, it is, but I'm not changing it. What I've done is I've basically said it's implicit in the structure. It is a parameter of the loop. It is no longer a control of the loop. It's a very subtle distinction, but a very important one. It affects how you think and how you reason about things. I've also got a tidy loop representation. This one's a lot easier. Start with an empty list and run through from 1 to 100, adding the square of the number from 1 to 100. That's quite nice. This is more declarative still. Okay, so effectively this is the most declarative. It's the idea of take the numbers from 1 to 100 and collect the square of each one. In fact, to square it, Groovy gives us a shortcut. I can just sort of say that. Once you're familiar with that, you're familiar with that. So basically what I've said is from 1 to 100, collect the squares of 1 to 100. That's very easy. It's almost exactly the same as the problem description. Oh, sure, there's a loop going on in there, but how many loops have you written in your life? Do you feel at this point in your life that you need to write more loops? You know, it's like, oh, I don't know, I've got a few more million loops inside me. I feel the need to exercise those before I die. No, you're done. You know what loops look like. And you know all of the kinds of loops that there are. There's the for each kind of loop. There's the finding loop. There's, you've got them. They're taking up wasted brain space. Imagine all the useful things you could do with the brain space they're taking up. All those images of cats and memes and stuff like that. Okay, there's bandwidth being wasted here. So the point here is we're going to commoditize this. We understand this. I'm happy that computers know how to loop. I'm good with that. I'm really quite happy to outsource that. Now, what we've got here, although it doesn't look immediately like it, because of the notation, is what is known as an intension in logic. The set of characteristics or properties by which the referent or reference of a given expression is determined. Put another way, the perspective of an intension of prime numbers is you describe them by their property. Non-trivial integral factors. Here are the properties that they have versus enumerating every single possibility. Typically, this is how you describe an intension. This is a set intention. This is the first 100 numbers written using just regular first-order predicate calculus. X is a natural number such that x is greater than or equal to 1 and less than or equal to 100, and what we're after is x squared. This is such a familiar form, and this is a highly declarative form. It's such a familiar form that we tend to write it differently. Select from where. Okay? In other words, this kind of logic is something that we've seen before, again and again. So if you're messing about with something like C#, then link in C# is directly in there. If you're messing about with Java 8 streams, it's not obvious that the language is there because select, we replace it by filter, and you suddenly see the language is there. If you're doing SQL, then this is blindingly obvious. This is logic programming. This is the essence of this. What we're doing is we're defining a relationship here, and we're saying, here's the constraint, and here's the things I want from that. Select from where. Plain and simple. Now, that gives rise in code, in most programming languages that support it, to the idea of a list comprehension. So we don't call it set intention, it's a set comprehension or a list intention or a list comprehension. Syntactic construct available in some programming languages for creating a list based on existing lists or other conditions. And it's that set builder or set comprehension notation. Now, I'll switch over to doing something in Haskell, and I guess because this is a Java-centric conference, if it makes you feel more comfortable, we can do exactly the same thing in Frege, which is a Haskell JVM. Yeah, more comfortable? Good. So what I'm going to do here is I've got a nice direct form of what I just wrote out, and there's a sort of a grooviness to it as well, in the sense I'm able to say, look, here's a list of the numbers 1 to 100. And I'm going to take x from this list, and I'm going to square all of them, which is quite cool. It's nice and simple, very, very direct. I could write a loop, but I don't think anybody needs to see the loop. I think we're good with that. But now it gets a little more interesting. If I have this kind of declarative approach, then it allows me to do some very interesting things. So what I'm going to do here is I'm going to shift this. I'm going to say, I would like a square of all the numbers, all the positive integers. So I'm going to take the natural numbers, which some people can say include 0. You can have a debate over that. The debates over whether or not 0 is a natural number are best had over a drink. You will reach the conclusion as you reach the bottom of the glass that emptiness and zeroness is a natural state of the universe, disappointingly, and therefore it is. So I don't want the 0 here. I just want 1 onwards. So I'm going to say I want all of them. How big is this set? Like really big. It's infinite. So, sure, let's try that in Frege. Oh, that works. So what we've got here is an infinite list. An infinite list of squares. We get 1, 4, 9, 16, 25, 36, it just goes on to infinity. I'm going to need a few more gigabytes on my laptop for that. But you don't have to worry about it. It turns out that infinity is one of those numbers that a number of people are afraid of. Not an infinite number of people, but a finite number of people are afraid of. But there's no need to be afraid of it because you can handle infinity. It turns out that as long as you only look at one thing at a time, you're good. Just don't look at it all at once. Because if you look into the abyss, it will look back at you. Okay? So just look at it one thing at a time. Then you can do it. This is the essence of lazy evaluation. Don't do it all at once. And that's how we deal with it. So at this point, we need a point of commitment. So what we've done is we've described the problem. I don't have an infinite loop. What I've done is I've just described, here is a thing. It's infinitely large. What would you like to look at? Well, I'd like to take the first 100, thank you very much. Done. At that point, there's a commitment. In fact, sometimes the way that people find a good way of thinking about some of these things is with a description. A description is kind of in the subjunctive mood. It's kind of like a wish. It's like, I would like you to consider, if there were an infinite list from 1 to infinity of squares, so square all of those, okay, right. And at this point, I'd like to commit to the first 100, and now we'd make it real. In other words, we describe the possibilities, and then we collapse the wave function. And we say, right, I'll have the first 100, thank you very much. Now, this kind of thinking is very, very tidy. I haven't had to do anything clever with the code. If I were doing this in a loop form, I'd have to figure out how to break out of an infinite loop, or rather, I'd have to maintain the loop. So we're going to apply this to a real problem. Yeah, we're going to move to FizzBuzz. Because we talked about drinking just now. Okay, FizzBuzz is a drinking game. Although I have seen it described as a game for teaching children arithmetic, I have no idea what the incentive is for a child. If you've only known of this as a programming interview question or as a coding kata, then I've got news for you. It's a drinking game. And the idea is very much, as said here, FizzBuzz was invented to avoid the awkwardness of realizing nobody in the room can binary search an array, especially after a couple of drinks. Because what you do is you count round in a group. Yeah, 1, 2, fizz, 4, buzz. Every time you hit a number divisible by 3, you replace it with fizz. Every time you hit one divisible by 5, it's buzz. Okay, 4, fizz, buzz, 7, 8, 9. Oops, I should have said fizz. At that point, you have a drink because you made a mistake, and the rest of the evening becomes predictable. Yeah. But when you hit anything divisible by 3 and 5, therefore divisible by 15, you replace it with FizzBuzz. Now, this is fairly straightforward to deal with in a sort of simple piece of code, and it has a nice, interesting, quirky property. You can say, well, I'm going to run it as an accumulator. I'm going to start with an empty result, empty string. Divisible by 3, I concatenate fizz. Divisible by 5, I concatenate buzz. And you feel really proud of yourself for having solved fizz, buzz, and FizzBuzz all in one go. Genius. But notice there's a really strong sequential dependency there. This is a very strong stateful dependency. You cannot reorder these, not that you want to, but this relates to larger pieces of code. There's a very strong imperative dependency, because when we say imperative, there's a suggestion that commands need to be issued in a particular sequence, and that is a form of coupling. When we talk about coupling, we normally think of relationships between types. Yeah? This class inherits from this other class, therefore there is coupling from the subclass to the superclass. This goes further. There is a temporal coupling. The sequence is critical. And there's plenty of state change going on. We've set stuff up. And then, just to mess it up a little bit, we say, well, yeah, what if there isn't a result? What if we haven't got fizz, buzz, or fizz, buzz? Oh, okay, now we need to do another action, and we'll concatenate the string form of the number. So we get 1, 2, 4, and so on. And so it's a nice, tidy solution, and actually in Groovy we can make it a bit tidier. We don't need to put return statements in. We can make it feel a little more functional. The idea that the last expression is the expression of the whole block. So that's quite nice, but it still doesn't change the fact there's an awful lot of sequential dependency. So another approach would be to specifically peel off each branch. Here, there is no sequential dependency. Okay, well, there's a subtle one. Do the 15 before you do anything else. But the idea is I don't repeat actions. Or do I? Well, I do, because 15 is, when I'm checking divisibility by 15, when I get divisibility by 3, in both cases I'm checking with respect to 3. It's 3 times 5. So I'm checking two things. That's still that little dependency there. Okay, so we could try doing something slightly different. This is exactly the same, but it makes you feel cleverer. Okay? Right? Because sometimes people say, Functional programming, it's expression-oriented programming. You don't have statements, because a statement is an instruction. You are stating a thing that you want to do. No. You need to just express yourself elegantly. So you say, yeah, the ternary operator, I have fully embraced. This is a single expression. And you feel really pleased with yourself. And your colleague is still sitting there going like, really? I do like the ternary expression, but obviously there is scope for abuse, and then you kind of have to elegantly format it. Okay, let's try something else. Okay, I'm going to stick with the ternary operator. But what I've done here, by the way, I'm not making any claims for efficiency at this point. What I want to do is I want to stretch your thinking, because sometimes people solve it, they go, oh yeah, FizzBuzz is really boring. In which case you have not kicked the problem around enough. Okay? You can make it really quite interesting. You can do some very strange stuff with it. It's such a small problem. Feel free to do that before you try it on your enterprise code. What am I doing here? I'm doing something slightly different here. I've inverted my model of thinking. What I've got here is I'm going to say there is a set of numbers that is divisible by 15. FizzBuzz, by the way, is normally defined between 1 and 100 as a problem. So the approach I'm going to take here is I'm going to say, look, there's the numbers that are multiples of 15. There's a set of numbers, 15, 30, 45, 60, so on. If n is in that set of numbers, it's FizzBuzz. There's another set of numbers, the ones that are divisible by 3. 3, 6, 9, 12. If n is in that set of numbers, there's still a little bit of sequential dependency there, but nonetheless, we've got something really quite nice here. There's a flow, there's a much clearer flow. What I'm doing here is I'm turning the problem around. I'm not saying, is it divisible by? I'm saying, is it a member of this set? If it's a member of this set, then it's one of these. If it's a member of that set, then it's one of these. And this kind of set-based thinking is actually one of the techniques that you can use to crack certain big data problems. What you're looking at is more than one way of looking at a problem. There is nothing more dangerous than an idea when you have only one idea. Yeah? Émile Auguste Chartier said that, and it's a great piece of advice. So we're changing the problem frame, and this is much more declarative at this level. Here's another one. Same kind of idea. What I'm going to do here is I'm going to take all of the fizzes, all of the buzzes, and all of the numbers. Okay, I'm going to say, look, fizzes. We've got an off by one thing to sort out, so I'll start off with an empty. And then I'm going to say, how do we define fizz? Well, all the fizzes that you need between 1 and 100, you don't need, number 1 doesn't need to be a fizz, so empty. Number 2 doesn't need to be a fizz, so empty. Number 3 does need to be a fizz, so fizz. Empty, empty, fizz. Keep repeating that. Same for buzzes. Empty, 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 buzz. Keep repeating that. And then you combine them. So now what you're going to do is 2 lookups, as we see in the function. I'll have the fizzes of n plus the buzzes of n. And if the number is 3, you get fizz plus empty. We're good. If the number is 5, you get empty plus buzz, which is good. If the number is 15, you get fizz plus buzz, which is good. But what if it's any of the others? The Elvis operator there allows us to deal with that. It's still a little bit of a sequential dependency, but hey, you know, we've got something here that's a really simple lookup. What we do is we just say, if there's nothing there, then take one of the numbers, please, which we've converted to string. We've just applied the operation over all of them. And again, there's that nice little spanning operator in Groovy, star dot, which just allows you to say, you know, those loops that you're so bored of applying, just do it, you know? Everybody knows what you mean. If you say apply to string to every single one of these, that's what we're doing. So we're done. It's a very nice, simple declarative form. And then it gets a bit crazy. I might not explain all of this one. This is a recent solution that I came across. It was originally in Haskell, and I translated it into a number of languages. This is one of the versions of it. This one has no branching in it at all. In other words, treat this as homework, if you get your head around it. What I'm going to do here is I'm going to create a lambda, or a block of code, a closure. If n is divisible by 3, I'm going to pass in the first block. Otherwise, I'm going to pass in whatever was passed in, it. So in other words, it becomes an identity operation. It just returns itself. Or it returns fizz plus the operation that's just been passed in. So we're passing operations around on an empty string. Buzz does this as well. And then we chain the whole lot together through composition at the bottom. And magic happens. The data flow and the control flow are identical. The information flow is very elegant. I'm not going to explain this further. There's a whole talk in that. But this is obviously a little bit too far. Okay? However, there is something we can pick up here. These are all examples. How did I know they worked? How did I know they worked? I know they worked because I tested them. Okay? And here is a declarative approach to thinking about testing. We get very, very used to the JUnit style of testing, which is actually, at one level, JUnit is very declarative. You offer test names. You don't instruct JUnit to go and test things. You declare the test. But it's still relatively imperative. Here's a piece of example data. We're going to do this, and then we're going to assert something. Yeah? Or here's a mock, and we're going to do a whole load of stuff with it. What I'm going to do is, for something like this, I can take a very different approach. I can declare my intent. I can say, here's the whole range, 1 to 100. I want the fizz buzz of everything from 1 to 100. And there are a set of true statements I can make about the result. And then what I want is that all of the statements that I make are true. And I can say, first of all, I'm going to list off a set of properties. Okay, so what I'm going to do, instead of saying, and this is the thing, when people do FizzBuzz as a coding kata, as a test-driven development kata, they often get the right result, but their tests are terrible. In other words, you end up with really bad tests, like test that 1 is 1, test that 2 is 2, test that 3 is fizz. That's great, except that it's not. That's not very intentional. You haven't declared your intent. You haven't stated the properties of the FizzBuzz domain. So what I'm going to do here is I'm going to say, look, every result we get is either FizzBuzz, or a decimal string between 1 and 100. So I constrain the result set. The next thing I'm going to do is I'm going to say every decimal result corresponds to its ordinal position. So in other words, the number 43 should be at position 43. Every third result starts with fizz, every fifth result ends with buzz. Notice we're now narrowing down, we're describing all the properties that make FizzBuzz FizzBuzz. Yeah, this is domain analysis, basically. What I'm doing is I'm describing a set of truths about the domain. I'm declaring it. This is a very declarative approach. Every 15th result is FizzBuzz. The ordinal position of every fizz is result is divisible by 3. The ordinal position, et cetera, et cetera. You need all 8. I haven't been able to reduce it beyond 8, but there we go. And then we can convert it into Groovy. And obviously that doesn't read quite as directly, but the idea is that it's still 1 for 1. There is the idea of a statement of truths. Now, I'm not suggesting you go out and throw away your Learist unit testing framework to go and do this. But what I want to do is offer you a bridge to what is sometimes known as property-style testing. Sometimes an example-based approach is very good, is the one that we want, and is particularly for stateful manipulation can be very, very helpful. But in other cases, what we want to do is approach a problem differently and describe it in terms of a set of constraints that bound what we're doing. Instead of telling it what we're going to do, we're going to say, here is the thing that we get that satisfies these is the right thing, which is a slightly different philosophy. But let's return to FizzBuzz. Let's just see how far we can take this before we switch to another thing. I want you to imagine, because we've already dealt with infinity. You're doing very well after lunch, I have to say. You've already dealt with infinity. So I want you to imagine there's an infinite number of fizzes. Okay, this is all the fizzes you will ever need. Not just the one that I did before, up to 100. This is blank, blank, fizz, blank, blank, fizz, blank, blank, fizz, forever. Okay, so that's one infinity. You handled the previous infinity so well, I trust you to handle another one. Because this is all that, well, this is out of range, actually. Come on, speak to me. Oh, the battery's dead. Ah, there it is. This is all the buzzes you're ever going to need. Blank, 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 buzz. Blank, 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 buzz. This is all the words you're ever going to need. What do I mean by words? This is all the words fizz, buzz, or fizz, buzz you're ever going to need. So this is blank, blank, fizz, blank, buzz, fizz, blank, blank, fizz, fizz, buzz, etc. So that's 3 infinities. Keep count. And this is all the numbers you're ever going to need. 1, 2, 3, 4, 5, 6. Yeah, 4 infinities. I'm doing well. Obviously, you need to be able to choose between them, and we're going to have a thing here, FizzBuzz, that combines everything. And that's going to be infinite as well. So there are 5 infinities up on screen. Yeah, who knew that HD could take that much? Okay, right. What I'm doing here is I'm doing this one in closure. What I've got here is I've defined fizzes as the cycle of blank blank fizz. Cycle just goes on forever. Because of lazy evaluation, it just says, if you were to ask me what this was, I would be able to tell you. But until you ask me, I'm not going to do any work. I'm just going to say, here it is. I cycle from here to infinity. The same for the buzzes. The words, well, it's a little bit of a hack here. No, it's an elegant workaround. It's not a hack at all. What I'm going to do is we'll start off with mapping. I'm going to stringifies. It converts something into its string form. And the way that I've done this is I've effectively mapped str across all the fizzes and buzzes. What I've done is I'm effectively doing a zip here. I'm taking fizz and buzz, and I'm going to go blank blank converts to blank, fizz blank converts to fizz, fizz buzz converts to fizz buzz, blank buzz converts to buzz. So I'm going to do all of that, and then I'm going to replace all of the blank ones with nil, which is null, which is nothing. You saw nothing except infinity. So now I've got an infinite number of words, and it's not just blank, it's null, null, fizz, null, buzz, fizz, etc., etc. Now I need all the numbers. Well, that one turns out to be fairly easy. I take the range, which is infinite, 0 onwards, but I don't need the first one, so I just say the rest. I don't want the head. And then I turn them all into strings. So it's 1, 2, 3, 4. And then finally, FizzBuzz allows me to use a little anonymous workaround here. I'm going to map. It turns out that or, this is an elegant hack. Yes. This is an elegant hack. Or, when it's presented with a null or a nil, treats it as false. And so what I'm going to do is I'm going to choose. If you give me nothing and a something, I will choose the something. Yeah, I don't just return true. I will return the second thing. So what I do is I select between the words and the numbers, which is quite nice. So now what I do is I go through. If I hit blank, the first word is nil. The first number is 1. Well, there's nothing in the first one, so I'll take the second one. Thank you very much. And the same for 2. And then I hit 3, words, that's fizz. And so therefore I take that one. That's the first one that satisfies the or. That's brilliant. So now we've got an infinite number, 5 infinities worth, but obviously we only need the first 100. And so we're done. Now what I like about this is that at no point on the screen do we have explicit branching. At no point do we sit there dividing by 3 or by 5. We've reframed the problem as a stream-based problem and a compositional one, which obviously gets us thinking in terms of, well, how far can we take this? Turns out we can take it quite a long way. As William Morgan observed a few years ago, I love functional programming. It takes smart people who would otherwise be competing with me and turns them into unemployable crazies. So something I enjoy doing is I like words. I run a page on Facebook called Word Friday, and I put an unusual word there every Friday, and then just linguistic and other language-related stuff during the week. So what I want to do is I want to present you with a useful word, because obviously you're going to need this every single day of the week, biquinary coded decimal. Yeah, if you see if you can just drop that into a conversation sometime. Okay. What is biquinary coded decimal? A system of representing numbers based on counting in 5s, with an additional indicator to show whether the count is in the first or second half of the decimal range. I wonder where that came from. Yeah? So where do we see this? It turns out we find it in abacus systems, not the abacus systems you give to your kids, but proper abacus systems. You get 5 beads and 2 beads. 5 beads and 2 beads. That's where this system, that's a biquinary coded decimal system. Some of the earliest computers, electrical and electromechanical, used biquinary coded decimal. Before everybody said, that's a hell of a phrase, biquinary. Why don't we just do binary? Yeah, that sounds much simpler. Yeah. But one of the classic ones is the Roman numeral system. Yeah, 1, 2, 3, 4, 5. Oh, V. Yeah, there we go. In fact, some people reckon it was actually based on the hands. You could do 1, 2, 3. You'd normally do 4, and then it was 5, and so on. And that's 10, that's 100, and so on. So you've got all these various ways of doing it. But this means we're going to try and figure out the other great problem of enterprise computing. How do you convert a number into its Roman numeral representation? There are businesses out there that are old enough that I can believe this might actually be a real problem. So what we're going to do is we're going to fully embrace the enterprise programming style. Hell yeah, I'm being paid by the line of code here. There we go, that's what it looks like. Yeah, if you are being paid by the line of code, ignore everything I've said in this talk. This is how you do it, and don't let anybody tell you otherwise. Okay. But what we do is we see regularity. We see regularity in this. How do we factor this out? And we've got this alternating if-while structure, and there's other elements there. It's just like, can I pull this out? Well, yes, show me your tables. What I'm going to do is I'm going to create a tabular system, and I'm going to run through it. And I've reduced the amount. I mean, this is actually, by the way, this is a general approach for many, many things. If you actually look closely, what you'll see there is a data part and a control part, and the data part is potentially changeable, plug-inable. But I'm going to take this a little bit further. We've got a for loop there. I feel that I can probably do a couple of other things with this that are a little more Groovy-esque, but also move this away from having control variables and accumulator variables that we actually change directly. So what I'm going to do is I'm going to replace my for loop with a dot each. I'm basically going to say there is a property. I'm going to apply an operation to the table itself. I'm going to apply code and pipe it through the table, effectively. Each time around the loop, I'm going to pull out a pair value and letters, and I'm going to operate on those and run the accumulator result until we get what we want. So now what I'm doing is I'm saying the table is the declarative structure. And this is the interesting thing, is when you look at the table, you can see the shape of the problem. Okay? And what I'm now going to do is I'm going to pipe data through it, bring it to life. So that's what the dot each is. It makes it more explicit. I can take it a step further and actually use an injection, which is a fold. And I really do have a pure pipeline there. I have no true variables in the classic sense of the word. Everything there, all of the results there are effectively immutable. I take stuff and I've created a mini pipeline where I project everything through and then it's folded together and I get the final result, which gives me the Roman numerals as I want it. So is this as far as we can take this problem? This is already very declarative. It's got a certain elegance to it. It may, if you're not familiar with Groovy, it may be less comfortable to read than perhaps one of the two previous versions. If you like, we're just tweaking it a little bit, but we've made a very nice pipeline here. I thought this was as far as you could take it, and then a friend of mine, John Jagger, showed me he'd stumbled across a solution on the web a couple of years back. He did it in Ruby, and then I sort of tweaked it into Python, and then a few other languages. Very different way of looking at it. That it's not an arithmetic problem at all. It's a symbolic problem. What I'm going to do is I'm going to turn the number into, I'm going to use proper full stream-based thinking. I'm going to turn the number into unary. You're not sure what unary is. It's like binary, but without the zero. In other words, 1 is I, 2 is II, 3 is III, and so on. So I'm going to convert the number into unary. Then I'm going to replace all of the 5 i's with v. Then I'm going to replace any residual 4 i's with iv. Then I'm going to, this is really, I'm not, again, no claims for efficiency, but wow, this is really easy to explain. What I've done is I've created a pipeline that structures the intent of the whole thing. I've embedded the data in the whole thing. What I find interesting about this one is, again, this is something that I could easily explain to a non-programmer by comparison with the previous approaches, which have an elegance to a programmer, but it's not obvious otherwise. And as many of you are probably more likely to be doing Java than Groovy, you'd like to know if you can do this in Java. Well, yes, you can, actually. You can get away with it, just about. But, yeah, it doesn't require too much extra. Now, we did Clojure before, so maybe I can do something really elegant in Clojure, because obviously everybody says, well, what about real functional programming? You know, full-on functional programming. Yeah, sure, let's do it. Let's resize that. It's kind of like this is like geese migrating in the winter. It's sort of a beautiful flocking formation, and It's like, yeah, that's what they mean by functional, isn't it? Everything's a function, and you call functions, and you take the results of functions. It's like, right, default functional programming out of the box makes a complete pig's ear of this. But that's the point, is that nobody talks about functional programming out of the box. They adapt it. They recognize there's more to it than just function application. So let's try a different approach. Here, we've got a structure that is based on function composition. Okay? Hence, that's what comp is up there for. From what I can tell, certain languages struggle with vowels and extra bits in words. So it's deafen, because apparently we're short of the right letters, and comp instead of composition, and fun instead of function, and func or whatever. But nonetheless, we have this idea, we take numerals, and what we've got here is a composition. What we do is, instead of saying apply the function, create a composition. In other words, you've got to reverse it a bit. First of all, we do the join, we repeat the number, we repeat I for a particular number, we join it all together, that gets us our unary number, and then we push it into the resulting composed function that is made up of all these funs are our lambdas, if it makes you feel more comfortable. And replace numerals I with V, I. Yeah, brilliant. I can tidy it a little bit. I can make it a little bit shorter. That's kind of looking it's looking a little bit more like a table. It's looking more like a structure than a doing thing, than an application, which is getting close. But I'm still unhappy with the fact that by default function composition happens in reverse. Because if you want to understand this, if you start reading from the top, then this is the wrong place. You need to start reading at the bottom. And you get a lot of functional programmers that have this kind of revisionist mindset. They say, oh yeah, it becomes natural to read from the end. No, really it doesn't. You know, if you are brought up in it, you are using a language, you are using a system of editing and a system of symbols, the Roman alphabet, that is based on top down, left to right. Okay? Fortunately, there's enough compositional structure in the language that I can replace this with that, and I'm also going to change the replace that I use, and we recover something very much like the Groovy version. That little arrow is a kind of threading operator. It allows you to bind things in a pipeline. And this recovers an intention here that the replace almost disappears as noise, and we're left with a table of structural transformations. And so therefore, if you like, the powerful side of functional programming is not just the functions, it's the ability to compose and restructure in certain things, but it is to recover this declarative idea. The first example I used with closure was not particularly declarative at all, which is why I say sometimes not all functional programming is declarative. Sometimes it looks in the sense that we want. Now, all of this is heading in the direction that I need to say, obviously, something about Java 8 streams. And so I will do this by picking on an example that I think is an interesting one. It's Zero Turnaround came out with a cheat sheet earlier this year for Java 8 streams. And there is a sort of an elegance to this that I think is quite nice. And it's the point that when you are able to hide the mechanics and state the effect, the very simple effects or desires that you have, and compose those together in a structure where you see primarily the intent, and then you say, there are details and I don't need to worry about them. And a good stream-based composition will look like that. A poor stream-based composition will be just as mysterious as anything else, and so it's not necessarily any worse. But there was a bug. There was actually a bug here, and so I tweeted, and it got fixed. Did you catch that? Watch again. And it got fixed. That's not right. In fact, the problem is the fix is also wrong, but for a different reason. Now, what I'm interested in is the fact that it was obvious by reading what the problem was, and it was partly because of the stream structure. So let's revisit this. Let's zoom in. What is the challenge here? The goal set is get the unique surnames in uppercase of the first 15 book authors that are 50 years old or older. I put a question mark there because is this what this does? This is the first thing they did. Let us just imagine that a library is simply a collection of books, which seems, kind of reasonable. A library is a collection of books. Take the stream of that. map every single book, replace every single book with its author. Okay, so we're interested in the authors. Pass that on, filter, it's a little bit ambiguous, select, or filter in, because sometimes people wonder, am I filtering in or filtering out? But select, for every author that you're getting, only select the ones where their age is 50 or over. Then limit that to 15, get the surname, shift it to uppercase, uniquify it, and then get a list out of it. Now the problem is that doesn't get the unique surnames in uppercase of the first 15 book authors that are 50 years or older. What it does is it gets the authors of the first 15 books. If you have the same author for the first 15 books, you haven't got the first 15 book authors, you've got it's a very subtle linguistic thing. You've ended up with a list of one already. Or rather, you're going to reduce to one, it's going to be the same author. You haven't eliminated duplicate surnames, you've actually eliminated duplicate authors. Not quite right. So let's look at the second one. Well, the second one, what you've ended up doing here is you've moved and uniquify, but you've ended up with get the first 15 unique surnames in uppercase of the book authors that are 50 years or older. Yeah, we get all the books, we get all the authors, 50 or over, we get the surnames, shift to uppercase, then uniquify those. That's the first 15 unique names on your bookshelf. If you happen to have multiple authors who have the same surname, then actually you've not quite met the specification. It turns out the correct solution is to uniquify in two places. Go across the bookshelf, go across the library, get the book authors, uniquify those. Now we are dealing with unique book authors. Doesn't matter if you've got 5 books with the same author, you've only got one author now. So uniquify the authors, limit that to 15, then shift surname, and then uniquify that. And finally we have the right result. Now, I mentioned this one to Trisha G. saw me do a version of this, and she's next door, funnily enough, talking about refactoring to Java 8. And she said, you know what would be really good is if you could show the full version of these. So let's show the full version. Because the observation that's being made here is that simple filters that can be arbitrarily changed are more easily reused and more robust than almost any other kind of code. You can see more easily whether or not something is right or wrong. Let's try that with while loops and things. Yeah, it's not going to fit on. That's the first thing you notice. Change the font size. Hey, right, there we go. So we've got, okay, that's the first one. This was the second version. And this is the correct version. Can you see the difference? I mean, it's obvious, isn't it? No, it isn't. You have to go into everything. You have to look up close at all of the detail before you figure out the differences between them. But also notice there's a fundamental shift in the style between there and there. That was actually just moving distinct further up or down. That it has this effect. From a coding point of view, if you ever wonder where legacy code comes from, it's the sheer resistance of a piece of code to being changed into something else. It's just like you say, I'd really like you to do this, and the code is there like a toddler going like, no. The point there is you want to move to a position where it becomes easy. And what we're saying here is not simply that it is easier to see, it is ultimately easier to work with. Indeed, clearly the pipeline model goes back a lot further. How much further? Oh, 1964 further. Doug McElroy came up with the whole idea of pipelines in 1964. It wasn't until about 1970 in Unix that it was fully adopted, and Ken Thompson said, you know what, we're going to use the pipe symbol, and the rest is history. But there's this idea, he said, look, we should have ways of coupling programs like garden hoses, screw in another segment when it becomes necessary to massage data in another way. And he unified this with I/O. It's a very profound idea, very simple, yet this compositional approach allows you to have an embedded imperative model, because every Unix process is imperative, but to chain them together in a way that is surprisingly stateless and highly declarative. You can reason about it very, very easily. So just for a bit of fun, I did have a go at this. I thought, you know what? I wonder if we can actually do the Roman numeral problem just using bash. The answer is yes. No, actually the answer is always 42. And it turns out, yeah, I create the first 2 lines there. It's a little bit subtle, the first 2 lines, but nonetheless, I create a simple unary representation, and then I use a declarative approach, regular expressions. They were at the beginning and they've come back again. And I replace everything, and suddenly I've got Roman numerals. So, it's not about the Roman numerals, it's not about FizzBuzz, it's not about the numbers 1 to 100. Ultimately, the advice that I'm trying to offer here is the advice that Elmore Leonard, the author, offered people. When you are writing code, what you're looking for is a style that allows you to leave out the bit that readers skip. The noise, the mechanics. The mechanics is all necessary. This is the ultimate message of any abstraction, is you want to abstract away stuff. But the declarative style is a way of thinking as well as a way of expressing yourself that is less about the doing and about saying here is. And I connect that with here is. It's about emphasizing the relationships between things. It's not simply a functional approach, and it's not simply pipelines. I've chosen that as a method of exploring. But it is about relating the parts rather than saying here is the doingness. Anyway, I hope that has been useful and waking you up. Thank you very much.